Hey guys, what's the crack? Ratwin Priyanna. Yeah, what's the crack of all the questions here? Team Sarah, you're currently at the gym. So you're just like gymming and doing physics at the same time. I know I said like doing exercise is really good because when you do exercise, it increases your frontal lobe capacity, it makes sure that you retain information better. Not sure if it's the same thing as being at the gym while trying to study. Oh wait, can you hear me? Wait, sorry. Did you hear a word I said there? Give me a yes, please, if you can hear me now. Help. Oh, thank you. Okay, good. So you couldn't hear what I was saying at the start now. Hi, Ishak. Hi, Carl. Did you hear me at the start? Natalie, you're good now. No, I was just saying at the start about how I'm not sure what Priyanna's on about. And I was saying about how team series is at the gym. And I was talking about how I told you guys like it's really good to do exercise because like increase your frontal lobe, it makes you smarter, like it makes you retain information better when you learn. But I'm not sure whether being at the gym and studying at the same time is the same thing. Is that research? But Team Sarah, you can let us know how it goes. No, Carl, no worries. You probably didn't hear me because I had the mic off. I'm still a newbie, eh? Oops. So, any crack for you guys this week? We're going to do nuclear physics today. So, a bit of E equals mc squared. Gravitational waves. Priyanna, you just type into type. Infamous equation, yeah. Oh, and I have some good news today. So two of the kids I taught last year, they were 1 mark off getting an A. Pardon me, and their papers got remarked yesterday and they finally got their A. So I'm feeling a pretty good mood about my year 13 kids right now. So at least it looks good because they did get into the unis they wanted, of course, but you know, some jobs do really care about what your A levels were. Okay, so fission and fusion. What do you know? You probably don't know much if you did combined science, but you did triple science. You probably have quite a good bit on you. So what do you think? What's the difference between fusion and fission? So what's the difference between fusion and fission? We had a good teacher, Carl. You're right. You're right. Keep chatting. Kai, if you have two quantum entangled particles billions light years apart and one moves, then another does the information transfer between them happen fast and light in the same particle? Kai, do you know I have like an Instagram thing? And so on Instagram, I did a like a Instagram clip about quantum entanglement because I find it fascinating. And remember we were talking about that show the other day. Last week we were talking about that show, and its name's gone. The three body problem. So that's Kai. Did you watch the three body problem? Is that how you started thinking about quantum entanglement? Hi, Ashna. So quantum entanglement, yes, Kai, that if they're billions of light years apart, if whatever happens to one happens to the other, but it's not to do with information traveling between them. So like it's not that information travels at the speed of light to them. Quantum entanglement is slightly different. So it's like a different type of physics. So the way that it's told to us is that the information does travel faster than speed of light, but the information is not actually traveling because they're entangled. What one does, the other one just knows. It's like mad physics, to be honest. Okay, fusion and fission. What are we thinking? Fusion is forming atomic nuclei and fission is split into two. Yep, fission, lovely. Fission is to do with splitting. Fusion is two more atoms come together. They fuse. Yeah, good job. Okay, so fusion, I don't know. You just came out of combined science, right? So fuse, you know when you learn in biology, the egg and the sperm fuse together, right? So fuse means things that like join together. So fusion is when we're joining stuff together. So exactly what Carl says there. So fusion is when we have two light nuclei and they fuse together. We join them together. So two light nuclei, we join them together to make one heavier nucleus. So one heavier nucleus, and then loads of energy is coming out. So loads of energy. And then fission is the opposite, like we said there, Nalia. Fission is when we have a large nucleus, so just in the reverse, We have a large nucleus, and then we split it up to two or more lighter nuclei, and then we release loads of energy. Yeah, so we're going to learn more about that. So that's what you did if you did triple. Okay, so what we're saying is here is when a nucleus is formed, energy is released. Okay, so when a nucleus is formed, energy gets released because there's going to be a change in their mass. Okay, and that's where Einstein's special relativity equation came from. So he says that when there's a change in mass, that mass and energy are equivalent. They're interchangeable. So there's a change in mass, there's always a change in energy. And the way to find out how much energy in joules is given off is because all we do is multiply by the speed of light squared. So the speed of light, remember, is 3 times 10 to the power of 8 meters per second. And that's a number you need to remember, right? It's going to take you forever to do this math in your paper if you're trying to find the numbers all the time. Okay, so it says use Einstein's equations. This is insignificant on large scales. Is Brooke alive? What? Can you not hear me no more? Are we good? So what we're saying here is, I want to know, you can hear me. Okay, you're just being odd. It's fine, we do physics, we're all odd. We're joke away. Okay, so what we're saying here is that there's a change in mass, right? And if there's a change in mass at the small size of the nuclei size, there's a large change in energy, right? So can you just prove that we don't use this equation when we're talking about large objects? Okay, so let's say I've got a torch and it radiates 10 watts, so the power is 10 watts of energy, and the time it does it for is 10 hours. Can you figure out how much energy is released by that? And then what would the mass of the torch change by? So this equation applies to everything, but we don't use it on large scale objects. So we don't always say like, oh, my torch has been on for 10 hours. Clearly it's going to be lighter. Technically it is lighter, but can you do the math to show how much lighter it is? And that's why we can just ignore that equation when we use large scale objects. Okay, so have a go. What energy is emitted by the torch? So what mass gets lost by the torch? I'm going to pop in the chat. What energy is emitted by the torch, and then what mass gets lost by the torch? So hopefully you're thinking, remember we want to learn some equations from GCSEs. Hopefully you're thinking power is energy divided by time. So how do we figure out how much energy there is there? So how much mass is released there? Kai says 4 times 10 to the power negative 12. Yeah, good job. Unit please, Kai, because that's awesome. Good job, that's really quick. So 4 times 10 to the negative 12, and our unit is kilograms. So hopefully you know what Kai did there. So to find the energy, all we've got to do is power times time. Kai, awesome. So power times time. So the power is 10 watts times the time is 10 hours. But remember, it has to be in seconds. So multiply by 60 to put it into minutes. Multiply 60 to put it into seconds. And then the energy you have there is 360,000 joules. Okay? So Natalie, I'm not sure what you missed there. So just have a wee look again. Maybe you forgot to put it into seconds. So what we have here is 360,000 joules. That's the energy. But I asked you how much mass does a torch get lost by then. So we said energy. Oh, you did. Grand. Energy equals mc squared. So all we do now is to find the mass. I take my energy and I have to divide by the speed of light squared. So you just have to take your number here and divide by 3 times 10 to the power of 8. And then don't forget the squared. To find out the mass lost by the torch is 4 times 10 to the negative 12 kilograms, right? So that's just me trying to show you that yes, everything does lose mass when it loses energy or transfers energy, right? So, but that because in such really large scale objects like a torch is going to lose 4 times 10 to the negative 12 kilograms. So it's not like I'm holding a torch and all of a sudden after it's been on for 10 hours, it's so much lighter. Okay, it's nothing to do with that because for the scale and the size of the torch to begin with, this mass is insignificant. But when we look at the mass of nuclei, it becomes really significant because the mass of nuclei is really small to begin with. Right, so that's what we're looking at today. Okay, so the first thing we're going to talk about is binding energy. Okay, so it says, I'm not sure, this is a topic that will come up when you start to learn about fission and fusion, so when you start to do nuclear physics. So I said last time, remember we did nuclear physics yesterday? On Thursday. This is a topic I teach towards the end of the year. But again, different teachers will teach things at different times of the year, right? So it says when a nucleus is formed, energy is released because there's a change in mass, right? We said that. So Einstein's theory of special relativity is this equation which allows us to relate the change in energy to the change in mass. binding energy is a definition you know for AQA. So binding energy is the amount of energy that we need to put in to remove a nucleon from the nucleus. So what's it saying is, say we've got a nucleus here, got loads of protons and neutrons inside it, protons, neutrons, protons, neutrons, protons, neutrons. The binding energy is how much energy we need to remove one nucleon, to remove one neutron from that nucleus. Okay? So iron 56 is the most stable. I don't know if you know this, but in star formation, iron 56 is the heaviest element that can be formed by fusion, right? Because fusion is what happens inside the sun. Fusion is when we join light nuclei to make a heavier nucleus. Because iron is so stable, it's the heaviest element that can be formed in stars in fusion. Okay? So anyway, that's just a random fact. If I'm telling you iron 56, so Fe 56 has got an atomic number of 26, and the mass of the whole nucleus is this number, can you figure out what is the binding energy? So what I'm asking you is, can you figure out what the change in mass is when that iron nucleus gets formed? So when you find out the change in mass, because I know the mass of the whole thing has that mass, but if I look down here, I can see it's made of 26 protons and 56 protons and neutrons. So what we need to find out is how much mass do we have of protons? How much mass do we have of our neutrons? What's that total mass? And what's the difference between this total mass and the mass of the nucleus? And that change in mass then, we're going to say E equals the change in mass, speed light squared. So you're going to find what that energy is in joules. But look, my answer line wants it in mega electron volts. Remember we practiced that last day. How do you get from joules to electron volts? Okay, so give it a go. So remember, binding energy is the energy to separate the nucleus into all its different nucleons. So that's why what we're trying to do is find out what is the mass of all the protons and the neutrons inside iron Fe5626. What's the mass difference between that and what the mass of the nucleus actually is, and that change in mass lets us calculate the energy. Yeah, right? So once we have it in joules, all we need to do, yeah, brilliant, really nice, Kai and Mally, is divide by 1.6 times 10 to the negative 19 to get it into electron volts. Okay? So that's the steps. So give it a go and then pop in the chat when you can figure it out. So again, our steps are iron has got 26 protons. So that mass there, if I just rub this out a second, oops, that mass there is going to be 26 times by the mass of a proton. So the mass of a proton is 1.673 times 10 to the negative 27. Then I got to figure out how many neutrons there are. So if I look at neutrons, remember I have to remember for physics because I don't get a data sheet. 56 minus 26 gives me a number of neutrons in the nucleus, which is 30. So now I got to do 30 multiplied by the mass of a neutron, which is 1.675 times 10 to the negative 27. So now that you have that, you want to find out what's that total mass there of protons and neutrons. And then what's the difference between that total mass and the mass of our nucleus. So when I did it, I found out the total mass of the protons and the neutrons was 9.374 times 10 to the minus 26 kilograms. So clearly you can see there are two different numbers of masses. And the difference in mass is because, remember we said anytime we split a nucleus up or anytime we form a nucleus, energy is getting released. So that's why the mass of them separately is different from the mass of the nucleus, because some energy has been released. So to calculate that energy released, we find the change in mass times the speed light squared. So hopefully you're thinking right now, I just need to take away these two numbers to find the change in mass. So it here says 1.63 times 10 to the minus 6, so everyone else give it a go. So what we're doing is 9.374 times 10 to the power of negative 26. We'll take away 9.288 times 10 to the negative 26 to find the change in mass is 8.6 times 10 to the negative 28 kilograms. So the change in that energy then is the change in the mass times the speed light squared. So I'd multiply by 3 times 10 to the power of 8 squared to get that the change in energy there is 7.74 times 10 to the negative 11 joules. Remember we said we want that in electron volts. So I have to divide by 1.6 times 10 to the negative 19. And I get the number 48375. 1, 2, 3, 4. I forgot to square it. So then to put that into, that's my number in electron volts, but my answer line says mega electron volts. So mega, remember, is 1 times 10 to the power 6. So now I have to divide that number by 1 times 10 to the power 6 to figure out what it is in mega electron volts. And I got a final answer. So someone else can pop it in to see what their answer is, but I got a final answer, 483.75 mega electron volts. Yeah, Nalia, beautiful. Yes, good job. Nice. So everyone else just like take your time, do the math and see if you agree. So Carol, you got the change to be 4.8375 times 10 to the negative 24. What would you have done wrong? You got 4.8375 times 10 to the negative 24. Is that your answer? Where's that your answer for? Are you okay, Carl, are you okay that Fe 26 means there's 26 protons? So that I do this number times 26 because it's my mass. And I've got 56 minus 26 protons, or neutrons, sorry. So that number is 30 neutrons. So find the total mass of our protons and neutrons using these numbers. And then when we have our total mass here, we can see that number is different from the mass of the nucleus. So we subtract those two numbers to find what the change in mass was. So that's what I got for the change in mass. And then so like Akir says, remember it's change in mass times speed of light squared. So they multiply by 3 times 10 to the power of 8 squared to see that a change in energy is 7.74 times 10 to the negative 11 joules. And then just be careful when you go into electron volts, you divide by 1.6 times 10 to the negative 19. Because of what Mali and Kai said there, 1 electron volt is 1.6 times 10 to the negative 19. Because Carl, you got the right number, it's just your magnitude's very off. Or, so let me know when you figured out what little bit of math there you did. What about everybody else? Are we happy? Iker, what do you think? Are you happy, Nelly? Mali, are we happy? Kai, are we happy? You got 0.25 instead of 0.75. Weird. Ah, okay, yeah. So 7.74. Ah, okay, Carl. Yeah, grand. Glad you found it. Nalia, no, you won't get the periodic table. It will give it to you like the way I have done here. So in your physics exam, they'll either write FE 5626. So we've got some more examples in this lesson showing you past paper questions. Or they'll do it like this, where they tell you mass number, atomic number in the brackets, right? So you just need to remember for physics, because you know in chemistry you get that little key. In chemistry, the top bit says like mass number, and then it says down here in brackets proton number. You don't get that key, we don't get the periodic table in physics. So you just need to remember that that bottom number there is our number of protons, and the top number there is number of protons and the number of neutrons. Yeah, so when you subtract the two numbers. So you just have to subtract the two numbers. Okay, are we happy to move on to more examples? Iker and Kai, you said you're good now, right? You figured it out? You're grand? Happy days. Look at you using the word grand. Right, okay, next one then is I've got lithium. So I want to know what the mass difference is in the lithium nucleus. Okay, so here I've given you the nucleus, I've given you the mass of the proton and the mass of the neutron, and I just wanted to put this here, I'll give you the numbers now. It's in U, okay? So what U means, it's called an atomic mass unit. ATM, atomic mass unit. No, atomic mass unit. Sorry, U is your atomic mass unit. So you need to find out what a U is in kilograms. So what you're supposed to do when you get this question is you go to your data sheet that you get given, and the front of your data sheet tells you that 1 U, and I forgot to tell it to you, 1 U, I'm going to have to put my data sheet, so hopefully you guys have a data sheet. I don't know if you guys keep it on your phone, but I keep mine on my phone. So 1 U on your data sheet, so on the data sheet of your periodic table, it's right at the bottom. It tells you 1 atomic mass unit is equal to 1.661 times 10 to the negative 27 kilograms. Okay, so now that you know what a U is, you're going to tell me what's the mass difference in the nucleus. So I've told you that the U, 7.01436 U is the mass of the nucleus. And I've told you what it is in U of proton, U of neutron. So when we're doing the same steps, you need to figure out lithium is 7.3. So what that tells me is, I remember the bottom numbers are protons. I've got 3 times the protons. And I have 4 times the neutrons. So we've got to figure out what that is in total. And I got 7.05652 U. So clearly that number is different from this number, because we know when a nucleus is formed or a nucleus is split, energy gets released. So now that's, both of those are in U. So you've got to find the change in the mass. And once you find the change in the mass, you're around. So you don't even need to know what U is actually. I give you too much information there. Yeah, Akir, beautiful. So if I asked you if all of these answers were in kilograms, that's when you'd have to use the U, but the answers weren't in kilograms. Yeah, Nalia, lovely, good job. So all we have to do then is we take our two numbers, so 7.05652 U, take away 7.01436 U, gives you a final answer of B. Brianna, if you can't stay with us, we're going to have to time you out, man. Why are you writing random stuff? So yeah, that was me telling you what a U was. So U is just a fast way of writing atomic mass unit. So you know in GCSE you were told the mass of a proton's 1, the mass of a neutron's 1. That is your relative mass, your atomic mass. But it's not really 1, it's 1 U. And 1 U means that many kilograms. But in physics, you're not just going to use 1, we're going to use the actual numbers. So that's why proton neutrons number is slightly different there. Yep, Carl Grand. Okay, nice. Okay, next thing we're going to talk about then is remember we said in the sun or in stars, the heaviest element that can be formed is iron. It's because it's the most stable element. So this graph shows you it. So we're just going to talk through this slide and then we're going to practice some questions on it. So it says, elements lighter than iron will undergo fusion. So we see that. Anything lighter than iron, so here's my nucleon number. Anything with a mass lighter than iron, they're always undergoing to go fusion on this side. Anything with a nucleon number heavier than iron is always undergoing to go fission. So remember, fission means they're very large, so what they do is going to split up into 2 or more lighter nuclei. And fusion means because they're so light, they're going to join together to try and make a heavier nucleus. Okay? But the problem is we're talking about nuclei right now. Okay? So remember, inside the nucleus, we have protons and neutrons. And so if we're trying to do fusion, I'm trying to get a nucleus to join with another nucleus. And hopefully you're thinking, protons have a positive charge. Protons have a positive charge. So I've got 2 positive things that I'm trying to join together. So what we're seeing here is there's going to be an electrostatic force of repulsion. There's an electrostatic force of repulsion trying to pull them apart. Those protons, those 2 nuclei, don't want to join together. So we have to go at very high speeds to overcome this electrostatic force of repulsion. Okay? So that's why it happens inside the sun. So it says solar energy is produced as a result of fusion. Because in fusion, we're taking 2 light nuclei, something like hydrogen, 2 light hydrogen, and we're fusing them together to make helium. So that's what happens in the sun. But it happens in the sun because the sun is such a high temperature, we can make these nuclei go really fast, so really high speeds, so that when they do collide together, we can overcome that force of repulsion and get them to stick together, get them to fuse together. Okay. Okay, so does anyone know the names of these? What's H2 and what's H3 called? Anyone know? So H1 is one on your periodic table. It's hydrogen, obviously. And then these 2 are called isotopes. You probably know that from GCSE chemistry. So isotopes. They're different atoms of the same element with the same number of protons but different numbers of neutrons. Yeah, so the smaller the nucleon, well, not always, right? So if you look here, this nucleon number is really small and this nuclear number is really large, but they have the same binding energy, right? It's more like where it is relative to iron. Heavier than iron its nucleon number is light, its binding energy is always less than iron. So to get more stable, more like iron, it's undergo fission. It'll split to form lighter things. Anything lighter than iron is less stable than iron. It's got lower binding energy. So those lighter things will try to make heavier things become more stable like iron. Yeah, good job. Deuterium or deuterium. Yeah, good job. So deuterium is hydrogen 2. Does anyone know the name for hydrogen 3? Begins with T. So we've got hydrogen 1, deuterium is hydrogen 2, and something beginning with T is hydrogen 3. Yeah, tritium, J and B. Yeah, and hello J and B. You haven't said hello yet. Good on you. Tritium. Yeah, good job. So you talk about hydrogen quite a lot on this topic. So hydrogen 1, deuterium, and tritium. That's the different isotopes we'll be using. Cat J and B is finally back. Okay, so right now on Earth, we know we have nuclear power plants. Nuclear power plants are able to undergo fission. So we're going to look at that later. Nuclear power plants is when we have really heavy nuclei and we split them up into lighter nuclei. So in fission, think nuclear power plants, they're buying in uranium-235. Okay? Nuclear fusion, like we just learned about, is when we need, like what happens in the sun, really high temperatures to overcome the electrostatic force or repulsion. How come we can't do that on Earth yet? Or we can't do it successfully on Earth yet? Does anyone know why? Or think about the problems. So why is it really difficult on Earth for us to get two lighter nuclei to fuse together to form a heavier nucleus in nuclear fusion because of those electrostatic force? How are we going to, so think about what we need to do on Earth to get that to happen. High temperature and pressure, good job. So what's the problem on Earth? We're trying to get really high temperatures and pressures. Yeah, loads of energy, right? So a significant amount of energy is needed, okay? And we know that anytime something collides with another object, energy is getting transferred there. It's getting lost. So if we have a container where we're trying to contain all of this light nuclei, as soon as they hit the walls of the container, they're going to cool down straight away. So we're losing energy straight away. So yeah, it costs a significant amount of money. Yeah, there is loads of research on it. So that's why I want to show you this slide. So the problem, so you do need to know about the problem. Plasma is, some people call it the fourth state of matter, but I wouldn't worry about that. Plasma is just what we call it. When the sun is a plasma. It's because everything is so high temperatures that all of the atoms, they get stripped of their electrons. So you always just get electrons and your nuclei left behind. So a plasma is just when you have loads of nucleuses, loads of nuclei and electrons. So in order to get that plasma, where we just want the nucleuses, we have to pass really high currents through it. And like we just said there before, we need to get really high temperatures to overcome that repulsion between the nuclei. So loads of energy. And then the way that we can stop it from hitting the walls of the container. So again, remember we said anytime it collides with the container, it's going to lose energy and cool down. The way to stop it colliding with the walls of the container is we keep it inside a magnetic field. So we keep it suspended in the middle of the container so it doesn't touch the walls of the container. Yeah, so you just need to know for AQI, you just need to know that because the high temperatures require loads of energy to overcome the electrostatic force of repulsion, and we know that we have to sustain it, contain it in a magnetic field so it doesn't touch the reactor walls. So yeah, this is me simplifying it as much as possible. And then I've got a link here for you if you want to look it up after. That's just showing you some of the research that's happening. Or maybe what time we're at. Well, I think it's interesting, so I'm going to show you. So, bear with. So, hopefully, maybe you can have a look at this link a bit. And maybe I'll post it in the chat as well. Can I post it in the chat? Yeah, if you click on that link, this shows you the world's largest and most advanced tokamak. Yes, somebody asked me, can we do it right now? So plasma is in jets. So remember, plasma, as just said, is when you strip all the electrons away from the atoms. So it's hotter than anywhere in the solar system. So this is just a page of information I thought was quite interesting, showing you that we are doing fusion on Earth right now, right? We are able to do it. It's just we're not making any money from it because of the high temperatures, trying to sustain that magnetic field. So we are able to do it. It's just not good enough right now that we're not going to build nuclear power plants right now that does fusion because the energy that we're getting output from it isn't higher. There's not a net output, right? So yeah, it just shows you here, like this is what it looks like inside it. So if I scroll down, you can see this it looks like a torus. So in the circle around it, that's where the magnetic field is. So those the plasma, when it's all super high temperatures, moving super fast, we're trying to get them to collide. None of it is touching any of these walls, the containers, because it's a big magnetic field in there as well. So it's quite cool what we're doing. We're doing it in the UK as well. So the UK is doing it, China's doing it, and there's quite a few other countries doing it. Okay, so next one we're talking about then is we're talking about fission. So we just said that if we're over here, we can see the nuclear number is really large, right? There's loads of protons and neutrons inside that nucleus, okay? Because there's so many protons and neutrons inside the nucleus, those protons are going to want to repel each other. So the electrostatic force of repulsion is quite strong in the nucleus, so it's really unstable. So the way for it to get stable is going to split into lighter nuclei to try to get a binding energy closer to that of iron, okay? So the way that we get to happen, so the way we get fission to happen, is we just said that uranium-235 is what we use in nuclear reactors, okay? So nuclear fission reactors, that's what we're able to do right now, okay? So nuclear fission reactors. The way to get the uranium-235, because we just dig it up from the ground, it's just a rock, we dig it from the ground, we fire a neutron at that uranium, and the neutron gets absorbed, and that's what starts the chain reaction. So then the large uranium nucleus splits into two lighter nuclei and releases loads more neutrons. Those new neutrons go on to hit more uranium-235s, and then that's a chain reaction, because then neutron gets absorbed, neutron gets absorbed, neutron gets absorbed. The uranium splits up to 2 or more lighter nuclei, and 3 or more neutrons always come out. And it's a bit of a weird one here to emphasize, but you do need to say that 3 or more neutrons are released. Okay, so in a nuclear fission reaction, 1 neutron hits 1 uranium, and then the uranium splits in 2 or more lighter nuclei, and 3 or more neutrons are released. Okay. Okay, so can you say, so now we're talking about, here's my fission reaction. I've got uranium-235, I'm firing a neutron at it, and that uranium is splitting up to lighter nuclei and 2 or more, but which is a 3, neutrons. Okay, so can you figure out what is that energy released? So what is the energy released? So again, I've given it to you in U. So remember, we know that 1 U, oh goodness, I've forgotten the number for 1 U. I'm going to have to look at my data sheet again. 1 U is 1.661 times 10 to the negative 27 kilograms. So what you need to do is you may split it up into your reactants, your products. Find out what the mass is in this side. Find out what the mass is in this side. Find out what the change in the mass is, and then use E equals mc squared to tell me what the change in that energy is, how much energy is released in that reaction. Okay, so give it a go. So I've told you the mass in U of uranium, the mass of U of barium, the mass in U of krypton, and the mass of the neutron. So find out the total mass in your reactants, what's your total mass in your products, and you should see there's a difference, there's a change in mass because energy is released. So then calculate how much energy then is released in that. And see if you can tell it to me in joules, just to get you started, to make sure you got the right answer. And then I want it in mega electron volts. Okay, so joules and mega electron volts. J and B, I'm hoping to join the effort someday. Maybe I'm cooked. Join the effort. Well, to be fair, what age are you? You're probably, well, you're 13, so you're probably what, like 17? They've been doing this research for years. Like, we're not talking years, right? So 100%, this research, yeah, is your guys' age. Because you think about it, once we get fusion to be stable and produce more energy output than energy input, once you get it started, there's a limited amount of energy. But then we have to be able to build. They're going to need experts in the field at all the countries trying to build the reactors in case problems happen, right? So yeah, like definitely your guys' age coming up. Not sure, but I don't think, maybe I could be proven wrong. I don't think in your guys' age we're going to have nuclear reactors, but at least have the research ready for the next building stage the year after you guys. Yeah, the maintenance. Yeah, because it's extremes amount of energy, right? And we have problems maintaining nuclear fission reactors. So imagine how hard it'd be maintaining a nuclear fusion reactor. Okay, is the total mass of the reactants 236052594? Yep, that's that number I got. Good job. So what you should have done is this number multiplied by U to get in kilograms. And then you have to add on this number multiplied by U to get in kilograms. So yeah, I got the same number as you. 236.052.594. And then over here, what we got is barium. So barium, you have to add it to krypton, and you have to add it to 2 neutrons. So that's U, sorry. Add it to 2 neutrons, and you get 234.857911 U. So now, just find the change in mass in U, and then put that into kilograms. You got 1.08 times 10 to the power 17 joules. 1.08. Are you sure 08? Because you're very close to what I got. Oh no, times 10 to the power 17. No, you're a bit off there. What you get in kilograms? Here. So hopefully we got the change in mass. So when we subtract those two numbers, the change in mass should be 1.194683 U. But then we need to put that into kilograms. So the change in mass there is 1.984 times 10 to the negative 27 kilograms. That's my change in mass in kilograms. Carl, you got 1.2 times 10 to the power 6. Bit off. Did you get the change in mass to be the same here? Or Carl? So we're happy, just to make sure we're good. You find the mass of uranium-235. You add that to 1 neutron, and that's the mass on this side. And the mass on your product side is we've got a barium. We have to add it to a krypton, and we have 2 neutrons. That number times by 2. It gives us this number. Then we subtract them to find what the change in mass is in U. But remember, that's in U, not kilograms. We know 1 U is this number. So I have to multiply those numbers together to figure out what it is in kilograms. You're good now, JMB? Yep. So we got in kilograms. Now we have the mass in kilograms. We multiply by the speed of light squared to get it into joules. So I've got that. So put it into joules. And then once you have it in joules, can you figure out again? Because this one you have to always use to give your answer in mega electron volts. Here, a positive 10. Fahim, you came onto this to see you, Garrick. So, Fahim, are you year 12 or are you GCSE? Yeah, here. Yeah, perfect. Good job. So, when we take this number now and you multiply by 3 times 10 to the power of 8, all squared, to get our answer in joules, hopefully we've got an answer of 1.7859 times 10 to the negative 10 joules. That's what I got. Yes, Nalia, beautiful. Good on you. Wait, Nalia, were you in the year 12 lesson today? Or am I tripping? Yes, here, beautiful, yes. So once we have it in joules, we want to put it into electron volts. So we have to divide by 1.6 times 10 to the negative 19 to put it into electron volts. No, I wasn't. Maybe I'm just spacing out. Or there could be more than one Nalia, which of course is a reasonable. So divide by 1.6 times 10 to the negative 19, put in electron volts. So I got 1116207260 electron volts. So I want it in mega electron volts. So I have to divide by 1 times 10 to the power 6. So we get an answer that I got exactly what egg here popped in there. 1116.2 mega electron volts. So as much energy we figured out was released when we undergo the nuclear fission. Carl, happy too. Happy days. Okay, good try, everyone. Okay. Have a go at this one now. So this one's a little bit different. Instead of me giving it to you in U, I've given it to you the binding energies of them. Okay? So it says uranium-236 this time, so different isotope, undergoes nuclear fission to produce barium, krypton, and 3 free neutrons. Okay? Calculate the energy released in this process. So this one's a little bit nicer. What is the energy released in this process? And then tell me, is it A, B, C, or D? So give it a go. So a little bit easier, but just make sure you read. So before I tell you what to do, have a look, read the table carefully. It says binding energy per nucleon, Fahim, you're in the GCSE summer course. Sunday course. You just thought, oh, come on, do some extra physics. Not even to see me, just to see Garrett, eh? Yes, I climbed the mountain to reach your cave, dear wizard. Oh dear. Chatterjee, hello. I've seen you all day today, eh? Don't lie, Fahim. Now you just feel bad now you didn't come to see me, don't you? Okay, so what we're saying here is we've given you the binding energy per nucleon. So it's 7.5 mega electron volts for 1 nucleon. But in uranium-236, hopefully you're figuring out I have 236 nucleons. So you've got to figure out what that is in mega electron volts. I've got 8.3 mega electron volts for barium, but it's per nucleon. I've got 144 nucleons. So figure out what that is in mega electron volts. And the krypton is 8.6 mega electron volts per nucleon, but I have 89 nucleons. So I'll be 89 to say what that number is in mega electron volts. Okay, and what it says is our uranium is going to produce our barium and our krypton and our neutrons. So we separate them, remember, into your reactants, your products. Find what the difference in energy is in the uranium side and the barium and the krypton side. And then pop in the chat, is it A, B, C, or D? And then tell me, why did I not tell you the binding energy per nucleon of a neutron? Why did we just ignore that? Why did I not include that? Or why do we not include that? Garrick does physics. Excuse me? Are we just done with me now? Is that what the crack is here? So 3730.6, you think D? Here, what does everyone else think? What do we think? Is this easier in A-level math? It depends where you're at. In year 12, I think everyone finds physics easier in year 12 than they do math, but in year 13, everyone finds math easier than physics. Or Kai, you can maybe not. Okay, so did we figure out? Hopefully, we this side I got 1170 mega electron volts, and for this number, I got, when you add them together, because they're both in the product side, I got 1960.6 mega electron volts. Yes, good job, Ikir, good job. Yes, nice fix. So then all we had to do was subtract the two of them. So then all you had to do was 1170, take away other way around, 1960.6, take away 1170 to get a final answer of 190.6 mega electron volts, which is option C. How's everyone else? Because I lost Naheem there, or not Naheem, sorry. I lost Nalia there. I lost JMB. Omar, hello, I didn't even see there. Hello, Omar. I lost Kai there. Nally, you got C, happy days. Your brain bugged out. You just took fat. No, it didn't. You're the one who got it right. You got C. Okay, so again, this is just me showing you. I'm just going to flip back a slide. This is me show you that it really matters here that you look at your tables, right? So if we look at our last table, they give it to us in U, atomic mass units, where this time they give it some binding energy per nucleon, right? So you'd be very careful that you read it very carefully. And then the whole reason for this one, this is a nicer one, because we can just ignore the neutrons, because a neutron is free, right? Because binding energy is the energy to separate a nucleon from the nucleus. Because the neutron is free, there is no binding energy of it, right? So that's why we can just ignore it. So this is a nicer version of the question. Okay, so moving on. Okay, again, it's a bit of me chatting, and then we're going to practice some questions that come up with this one, okay? Nuclear reactors, they're asking a lot more about recently, okay? And they're asking really specific questions about them, okay? So this, hopefully, you'll have printed out the booklet. This is everything I've summarized that you need to know, right? And if you know everything on this slide, you'll be grand. But you have to literally know everything. It's not like you can just skip out a word, okay? So this is me condensing all the information I found on it that you need to know, okay? So nuclear reactors, the ones we have right now are obviously fission ones, because we're working on the fusion ones, but we don't have them yet. So our nuclear fission reactor, hopefully you can see here, I've got control rods. Our control rods are what we can raise and lower, okay? So control rods are what we can raise and lower. And then we've got the fuel rods, and the fuel rods, so for the fuel is, so that's their fuel, is uranium-235. Yeah, it seems like a lot, right? But it's probably because it's just a lot of typing. But I'm going to talk through it, and then hopefully you'll see that it's actually okay. Okay, so inside the reactor fuel, we first have to enrich it, okay? So everyone probably knows that there's carbon-12 in the universe and there's carbon-13, okay? But there's more carbon-12 in the universe than there is carbon-13. Same thing with uranium. If I go digging in the ground, there is uranium-235 and there is uranium-238, okay? Uranium-235 is what we want to use in our nuclear reactors. But if I go digging it all up, I'm not going to get a lot of uranium-235. I'm going to get loads of uranium-238. So what we have to do is we have to enrich it with more uranium-235. So basically that means we want to separate out the uranium-238 and try to put in more uranium-235. Okay? The control rods are these things we just said we can put them in and put them out. Okay? They need to be made of non-fissionable material, right? Because this is a nuclear fusion reactor. We don't want fusion to happen. Okay? It's a nuclear fusion reactor. We don't want the control rods to undergo fusion. So we want them to be inert. So inert is unreactive. An example of what they can be made of is boron. So boron control rods. And you do need to know that they could be made of boron. What we want to make sure is that we want to make sure this reaction doesn't go out of control. Okay? Because we just said, remember, the uranium-235, what we said happens is we hit it with a neutron, and that uranium splits into your lighter nuclei and more neutrons, which then go on to hit more uranium-235. So we need to make sure this reaction doesn't get out of control, because if it goes out of control, that's when meltdown happens. Okay? So that's why we need to have the control rods so that we can lower them to absorb some of these neutrons so they won't go on to cause further fission. Okay? So our control rods, we can lower them and put them all the way in if the reaction is going too much, so then we absorb the neutrons. But if the reaction is going too slow, we can pull them all back out, so then the neutrons, there's more of them there, able to go on and cause further fission. Okay, so control rods, we don't want them to be fissionable, we want them to be unreactive, and want them made in boron. Okay, so it says, some neutrons, however, are traveling too fast. So if this neutron is traveling too fast, too high speeds, it's not going to be able to get absorbed by the uranium-235. So clearly we need to slow them down. So the way that we slow them down is that we're going to have a thing called a moderator. Okay, so we can see here, water is the moderator here. Okay, so what that means is the moderator means that when say I've got an H2O molecule, when my neutron hits the moderator, it's going to get slowed down. So that water absorbs some of the energy. But remember, it's non-fissionable because I don't want it to absorb the neutron. I just want it to slow it down. Okay, so again, we have a moderator, so we can slow them down, become firm on neutrons. So because we need them to be firm on neutrons for the uranium to absorb it, and also if I slow them down, they spend more time in the reactor because they're traveling slower, so it's more likely that I can get fission to occur. Okay, so next thing you want to know is we either make it from graphite or water. Sometimes it's called hard water, but you don't have to write hard water, you can write water. Okay, so the next thing said the moderator is going to heat up, right? So we just said this water is absorbing all of those neutrons, it's going to heat up. Okay, so I need to remove that heat energy. So that's why we have a coolant, makes sense. A coolant is going to cool it down. So the coolant now is going to take all that heat energy and absorb it. Okay, so that the heat is going to get cooled down. So when we do that, we want to make sure it's non-flammable, it's non-corrosive, it's not undergoing go fission, and the key one is a high specific heat capacity, so that it can absorb all that heat energy and transfer elsewhere. Okay, so again, just be clear and just pop in the chat so we're listening. Really quickly, can you tell me one material that the control rods are made of? Pop in the chat. What's one material that control rods are made of? Yeah, boron. Good job. Right, boron. Carbon. We haven't even said the word carbon, Carl. Not Carl, sorry, Kai. I apologize, Carl. Yeah, boron. Nalia, where? I don't think I've written carbon once. Oh, I wrote carbon dioxide. Fair, but yeah, boron, right? Control rods are made of boron. Controls are made of boron. Tell me what the moderator can be made of. So what is the, question 2 is, what is the moderator made of? So what is the moderator made of? Yeah, it could be water. Good job. Yeah, water. Good job. So water's a nice one because we can use water as the moderator and we can use it as the coolant. And then the other option was graphite. Okay. So water's a nice one to remember because we use it as the moderator or as the coolant. We use it both. And in this example, I have my picture. It's used as both. Okay. Okay. So just before we go on to see the exam questions then, we know that uncontrolled reactions can kill people, right? Can harm people. Because remember, the control rods, they can go down. We can lower them so we absorb all of the neutrons so they can't go on. We'll absorb these neutrons so they can't go on to collide with any more uranium. And that will slow our reaction down, slow the amount of energy produced. Or if the reaction is going too slow, we're going to raise the control rods up so that we have all these neutrons free to cause more collisions. Okay? So can you tell me what is an advantage of using nuclear fission reactors, nuclear reactors, and what is a disadvantage of using our nuclear reactors? Pop in the chat. What's an advantage of our nuclear reactors and what's a disadvantage? Garrick, it's strange giving advice because I barely revise myself. Yeah, it can harm people because it's not controlled. Yeah, but how does it harm people? Right, yeah, the advantage is there's loads of energy. Loads of energy. You don't need to know this fact, but I think it's quite interesting. 1 kilogram of uranium, so uranium-235, 1 kilogram of uranium gives out this, 1 kilogram of uranium gives out the same power, so you don't need to know this fact, I just think it's interesting to learn, gives out the same power of 25 tons of coal in a fossil fuel power station. So to 1 kilogram of uranium, so in a nuclear power station, gives us the same power output as roughly 25 tons of coal in a fossil fuel power station, right? So it's a significant amount of energy we get out from it. Yeah, so the disadvantages we're saying is harm people, but how does it harm people? So like what does that sign mean? Guess what I'm asking. Oh, Kai, yeah, beautiful. We're getting radioactive waste. Okay, and what do we have to do then? What's the problem with that radioactive waste? Right? They might have really long half-lives. Good job. So they'll stay around for a really long time. So what are we spending? Disposal, GMB, that's what I wanted. Good job. So we have to dispose of these materials, these radioactive materials. And you need to know about the disposal process. Okay, so again, the nuclear physics is kind of quite a lot bit of learning. Again, because oh no, we're not going to put them on landfill sites. So the nuclear physics is something you need to know about how we're going to dispose them. Can anyone give a guess? How do we dispose of the waste? Yeah, underground, deep underground. Do we put it anywhere underground? Like, am I going to bury it in Florida? Am I going to bury it in, I don't know where the fault lines are. Am I going to bury it near a fault line, basically? Hopefully you're thinking, obviously not. Because we don't want to, so we all know a wee bit of geography. This is terrible geography, but we know that the Earth is split up into tectonic plates, and these tectonic plates move over each other. So I'm not going to bury my radioactive waste here, because then the plates move, I might release that radioactive waste. Right, so yeah, we want to put it in uninhabited areas, low population areas, really deep underground. We want to put them in geographical, stable locations. Yeah, good job. Does anyone know what the containers are made of that we bury them in? So I've got some radioactive waste. I have to put it in some tank. What are we going to make the containers of? What material normally? Yeah, so we want to keep them, lead and contrary, steel tanks, and aluminium. Because remember, aluminium, beta particles can't get through aluminium. So just going to skip this for a second. So this is how we store it. Okay, so One thing we want to do is, like you all just said, we keep it in thick lead, because we know thick lead reduces the amount of gamma rays that comes out. Another thing we do is we put it in these things called cooling ponds. That's me trying to show you a picture there. So what we do is, as soon as the radioactive waste is finished from the power station, we put it straight into cooling ponds. So this is just a big massive tank of water. So underground, he's standing on top of it there. Underneath him is just big tanks of water, and they put the radioactive rods. So each one of these is just a really long cylinder. Because remember we said there's the fuel rods. So what they do is they take the fuel rods and they put them in here. So you can see like that's the top of a fuel rod, and it goes really deep underneath him. So you just insert all these fuel rods here, and the fuel rods are in these cooling ponds because the water is able to, first of all, cool the temperature down and absorb some of that radiation. Again, we said we want to bury it deep underground in geographical stable areas, geographical stable areas. Remote handling, hopefully everyone's okay with that one, but clearly it's not a human's going to go lift with their hands this fuel rod and slot it in the ground, right? We want to use robots, right? Because I don't want to be in contact with this radiation. So remote handling, we make sure they wear protective clothing, so like lead-lined clothing. And another thing we want to do is we want to make sure that everything is solid, because if I have any gases or liquids, they're more likely to leak into the environment and be dangerous for our environment. Okay, so just to make sure we're good, a little bit more math then. Actually, we'll skip this one because you see that you're quite good at the math. We'll do this one. So 1 and 2, for the sake of time, do 1 and 2. And for the sake of time, actually, to be fair, we've got a year 13 lessons now. So I'm going to tap out because LaJoy's got a chemistry lesson. But you guys have been awesome. Hi, Gurjot. Sorry, it's been late. So again, we're just remembering about how we're going to store our radioactive waste. Okay? So last lesson's on Thursday. So maybe just have a go at this and we can talk about it on Thursday, okay? So I'll leave this slide up for you guys. All right, have a lovely day. Good job today. See you Thursday.